So as part 3 on our series, we're going to now consider the family of the Poncelet family of 5 periodics interscribed between two non-concentric ellipses, non-axis aligned. But I want to consider this different manifestation of 5 periodics in the Euclidean plane where the trajectory is self-intersected. Okay. Now I want to define the three diagonals in the following way. First one is going from P1 to P2. You can see here that this is coinciding with a trajectory segment. The second one is going from P1 to P5. And then the cross diagonal is going from P3 to P4, just as before. Okay. Now you can think of these three vertices here also being inscribed in the ellipse, and you could connect them. Okay. And I believe there is a theorem that shows that if you actually connected P1 to P3, P3 to P5, P5 to P2, and P2 to P4, and you close this polygon here, this five-gon inscribed in the ellipse, its cosec would also be an ellipse. So these two families are really the same, the self-intersected and the non-self-intersected from a projective standpoint. But let's just focus on the Euclidean phenomenon here. So you can think of these three diagonals that I just defined as being diagonals that are internal to this polygon, this sort of simple polygon connecting P1 to P3 to P5 to P2 and P4 in the same way that I just defined them in the previous video, right? So I have these three diagonals, and I can play the same game. What's happening to my sum of cross ratios as I traverse this family for this particular A, B, C, D arrangement? We're going to get the same results. Only the product is actually being conserved here, 18.865. Let's change the arrangement now to the second arrangement. Now I have A, B, D, C, and now I get that both product and sum are being conserved. The sum continues to be 3 units above the product. Let's go, so let's just watch this for a second. Sum conserved at 3.053, product conserved at 0.053, 3 units below the sum. Let's go to the third cross ratio arrangement, A, C, B, D. What do I get here? Only the product is conserved. Notice that this product is the same value as the previous arrangement. Okay, let's go to the fourth arrangement of 4 collinear points. Now we get that both are conserved and they're both equal for some reason. So let's see this very interesting situation here. Here we have a situation of ACDV where the product is 18.865 and the sum is 15.865. Okay, so the product is 3 units above the sum, and the arrangement is ACDV. Now, if you allow me, I'll go back to a previous system where the trajectory was not self-intersecting. Okay, it's going to be a 5 periodic, non-self-intersecting. This one over here, completely different, in some sense from the previous one, but I'm keeping the same arrangement, ACDV. Okay, now look at what's happening here. I'm getting the same phenomenon, however, in the sense that the product is being conserved and the sum is being conserved, but the product is 3 units above the sum. Okay, now you're going to recall that there was another arrangement. Let's see if I can find it here. Oh, maybe it's not here. Okay, yeah, so let's just stick with this arrangement here. So this arrangement is giving me the same property, okay, as the arrangement with the self-intersecting case. So I'm also getting here 3 units product above, invariant product above the invariant sum. So it seems like this phenomenon is common. So this particular arrangement for these particular diagonals, this particular 5 periodic family, be it self-intersecting or not, we're going to get the same thing. And of course the values themselves are changing based on the specific relationship between these two ellipses. Of course, it would be a curious thing for us to go back to the non-intersecting case over here and say, okay, now I can draw a, so if I take the 5 points on the non-intersecting case, P1, P2, P3, P4, P5, you can imagine that the diagonals, the internal diagonals to this system here are going to define for me a pentagram. So I can build a pentagram using the 5 vertices here, and this would be 3 edges of that pentagram, right? So let's see how we would build this pentagram. I would go from P1 to P3, first diagonal, P3 to P5, second diagonal, not shown here, then P5 to P2, then P2 to P4, and then close the pentagram on P1. So it looks like this non-self-intersected, a simple five-gon here, is pregnant with that pentagon. And these three diagonals that you're seeing here are precisely the three diagonals chosen in the self-intersecting case. Let's go back to it. Okay, so I start from point P1, and I choose these two trajectory sides emanating from P1, and one cross side here from P3 to P4. And what I'm going to get is the same phenomenon. Even though the geometry has changed here a little bit, you got different values for the numbers, but it looks like the distance or the difference between product to sum is 3, both in this case, and let me just stress that we're using ACDB, okay, as the ordering or the labeling of vertices in the cross diagonal. So we're getting the same difference of 3 either in the self-intersected case or the non-self-intersected case, which I'm going to show here. So there it is. So these two arrangements are really similar. What this is pointing to, and I'm not going to cover this in this video, but we can be pretty sure this is going to be the case, is that in the self-intersecting case that I will put on the screen here in a minute, here's a self-intersecting case, there's going to be some arrangement if you define the two emanating diagonals, quote unquote, as leaving from P1 to P3 and P1 to P4, and you consider as a cross diagonal something that is not being shown here. Let's see if I can define this. 1, 2, the P2 to P5 segment. Okay, so this is going to be something really interesting. If you go back to the non-self-intersecting case, and I could define a cross ratio. So let's go back to this. I'm going to make my first diagonal be P1 to P5, the second one be P1 to P2, and the third one, which is not parallel, P3 to P4, which is going to intersect with these first two diagonals in two distinct points. So I'm going to have my quadruple of points again, A, B, C, D, and they're all going to lie on P3, P4, okay? And this quadruple is going to have certainly nice cross ratio sum and cross ratio product properties. Okay, so it looks like we're making a statement here about two segments of 5 periodics, sort of two segments that is incident on P1, and the third segment, and computing the intersections of this third segment with the first two segments and getting 4 points that will lie, you're going to have P4, P3, and two exterior points. So your B and C are going to be exterior here, and this is A and B, and you're going to get these 4 collinear points along P3, P4, and they're going to carry under some arrangement, some quadruple arrangement, constant, both constant sum and constant product. I'm just in a way assuming this is going to happen. It's kind of somewhat obvious from what we're doing here, because we're seeing the sort of correspondence between the non-intersecting case and the intersecting flat periodic case, and how the diagonals and sidelines of each one of these cases relate to one another. So I guess I'm just going to close with this. This video is about the relationship between these two families. They're really the same family if you consider the trajectory segments of this one as diagonals of the previous one. Okay, thank you. I'll see you in the next video.